Hi everyone, in this video we're going to go over 1.2 day 2 in which we test relations for symmetry, both graphically and analytically. One skill that we're going to bring back today that will help us in testing for symmetry is finding the intercepts of functions and relations. So we're going to go through that in a few examples here, looking for both the x-intercepts and the y-intercepts. One important thing to remind ourselves is that with x-intercepts, the y-coordinate is always going to be equal to 0, and for the y-intercepts, the x-coordinate will always be equal to 0. So if I look at this function on the left, first I'm going to plug in y is equal to 0, and that's going to help me find my x-intercepts. So into my equation, I'm going to plug in 0 for y. I'm going to get 4 times 0 squared minus 9x squared is equal to 36. Solving for x now, we just end up with 0 over on our first term. I'm going to go ahead and divide by negative 9. I get x squared is equal to negative 4. My next step algebraically would be to take the square root of both sides, but we run into an issue because we can't take the square root of a negative number. This would give us an imaginary number. So in this case, this first equation does not have any real x-intercepts. To test for my y-intercepts, I'm going to do a similar process, but this time I'm going to plug in 0 for x. So if I plug in 0 for x, I'm going to end up with 2y squared is equal to 36. When I divide both sides by 4, I get y squared is equal to 9, and then taking the square root of that will give me a real value for my y-intercepts. I'm going to have plus or minus the square root of 9, which is plus or minus 3. So I'm going to have two intercepts here, 0, negative 3, as well as 0, positive 3. I'd like you to pause the video and try finding the intercepts for the equation on the right. Can you solve for both the x-intercepts and the y-intercepts? Here are the answers for these intercepts. The x-intercept over here is going to present a little bit more of a challenge. When we plug in y equals 0, we have to factor the expression on the right. My first step was to take out a GCF of x, leaving me with x times x squared minus 1, and then I went and factored that quadratic into x plus 1 times x minus 1. Once I have each of these factored, I can solve for x by setting each of the factors equal to 0, so I actually end up with 3 x-intercepts. One at the origin, 0, 0, one at the point 1, 0, and the third one is at negative 1, 0. Finding the y-intercept was much more efficient. When I plugged in 0 for x, I quickly found that the only y-intercept was at 0. So the origin 0, 0 counts as both an x-intercept and a y-intercept. We're going to bring back this idea of finding our intercepts when we solve for symmetry analytically. So first let's revisit the idea of symmetry, and let's take a look at 3 different equations and their graphs and how we know which type of symmetry we have. So the first one is y equals plus or minus the square root of x. So the positive square root of x would start at the origin and go up like this. The negative square root of x is going to be the same thing, but down in the negative direction. Not a function, but it is a relation. When we test for symmetry graphically, what we're going to be looking for is it symmetrical about one of our axes or the origin? We have x-axis symmetry because it's reflected about this x-axis. We can also look for points on our graph, and for every xy coordinate, we should also have a coordinate with the same x coordinate, but the opposite y coordinate. So here I have the point 4, 2. I should also have the point 4 comma negative 2 on my graph in order for those to have x-axis symmetry. Another one to look at, in the middle here we have y is equal to negative times the absolute value of x. This is going to have y-axis symmetry because it's going to be symmetrical about the y-axis. So our absolute value function will take the form of a v. If I'm multiplying that by negative 1 on the outside, it's going to be reflected upside down. So it will look something like this. The last one here is the graph of our trig function, sine of x. We're going to get more into this one next semester. This one takes the shape of a wave. It has origin symmetry. If I sketch this out, the sine function doesn't have nice integer values, but it's going to be something like this. And we can similarly test for origin symmetry with the points. For every x, y coordinate, we should also have an ordered pair with the opposite negative x, negative y coordinates. So let's say for simplicity's sake, this coordinate is at 2, 1. We should also have a coordinate at negative 2, negative 1. So the first test we're going to look at is the graph test, testing for symmetry graphically. It's definitely more involved of the two methods. The first step is going to be to find our x and our y intercepts. So I'm going to start with the x-intercepts. This is where y is equal to 0. So up at the top, I'm going to plug in 0 for y. I get 4x squared is equal to 32, which gives us x squared is equal to 8. Which means when I take the square root, I'm going to get plus or minus the square root of 8. If you want to simplify that, you get plus or minus 2 square roots of 2. So we have two x-intercepts. Now, in order to test for symmetry, we're going to take a sample point. So I'm going to avoid these intercepts, and I'm going to pick a point that's going to be nice to work with. So something that has a nice x value. So let's plug in x equals 1 and see what we get. We get 4 times 1 squared plus 2y squared is equal to 32. That's going to give me 4. So if I subtract 4 from both sides, I get 2y squared is equal to 28. Dividing by 2, I get y squared is equal to 14, which means y is going to be equal to plus or minus the square root of 14. So I'm going to pick one of those two y values. Let's use positive square root of 14. So this sample point here, 1 comma the square root of 14, is going to be what I'm going to use to test for symmetry. And how I'm going to test for symmetry is I'm going to look for those points that would cause y-axis symmetry, x-axis symmetry, or origin symmetry. So I'm going to ask myself, does the point exist with that negative x coordinate, so is -1, and the same y coordinate, square root of 14, is that a part of my graph? And to find out, I'm going to plug in -1. So if I plug in -1 for x, I get 4 times -1 squared plus 2y squared is equal to 32. So that's going to give me still 4 plus 2y squared is equal to 32. Continuing to solve for y, we end up with y squared is equal to 14, which means y is equal to plus or minus the square root of 14, which means that yes, -1 comma square root of 14 is on my graph. So I know it has a y-axis symmetry. Now I'm going to test for the second type of symmetry. So this first one, that was y-axis. Second one now, this is going to be x-axis. And I'm going to ask myself, is the point 1 negative square root of 14 on my graph? Right? Same x-coordinate, opposite y-coordinate. We already know that that's on our graph because of this sample point. When we algebraically solved for y, we also got negative square roots of 14. So the answer is yes, 1 comma negative square roots of 14 is on our graph. Last one is the origin symmetry. We want to know, is -1 negative square roots of 14 on our graph? We know that from our second plugging in. When we plugged in -1, we did get the output of negative square root of 14 as well. So yes, we have origin symmetry as well. So we can plot these, our original sample point, as well as the 3 other points we generated. The square root of 14 is going to be between 3 and 4, so here's the sample point. 1 is our x-coordinate. Then we saw that -1 square root of 14. Then we had 1 negative square roots of 14. And finally, -1 negative square roots of 14. If we sketch what this relation would look like, I can tell it's not a function because it would fail the vertical line test. We have something that looks like an oval. But we can confidently say that we've tested graphically. It does have x-axis, y-axis, and origin symmetry. So when we tested for symmetry graphically, we were using points on our graph. We had sample points, we had our intercepts, we were finding actual coordinates, and we were sketching that graph to test for symmetry. When we test for symmetry analytically, we're going to stick to variables. We're not going to find any actual coordinates, any actual points on this graph. So we're going to use just this equation, y equals x cubed minus x. Now, if this were to have x-axis symmetry, it would mean that the coordinates x comma negative y would exist on this graph. So what we're going to do is we're going to take this negative y and I'm going to plug it in to that equation. So this would become negative y is equal to x cubed minus x. I'm going to rearrange this for y, and if it matches where we started, if it matches our original equation, we know it has x-axis symmetry. So I'm going to divide everything by -1. I get y is equal to negative x cubed plus x. Now I compare it. Does this match my original equation? They are not the same, so no, this does not have x-axis symmetry. I'm going to repeat this process for my other types of symmetry, but this time with y-axis symmetry, I'm going to replace x with negative x. My equation then would be y is equal to negative x cubed minus negative x. I'm going to simplify solving for y. I already have y by itself and it's positive, so I'm just going to clean up this right-hand side. Negative x cubed is going to leave me with a negative x cubed. Minus a negative x leaves me with plus x. Comparing this to the original, they are definitely not the same, so no, this does not have y-axis symmetry. Last but not least, origin symmetry. We're going to replace both the x and the y variables with negative x and negative y. We're going to simplify here. I get negative y is equal to negative x cubed plus x. When I solve for y by dividing everything by negative 1, I'm left with y is equal to x cubed minus x. This now is the one that matches my original. Since those are the same, we can say yes, this has origin symmetry. It is possible for it to have none of the above, or just one or more than one.